All right, good morning, everyone. My name is Mildred, and in today's session, we're going to look at databases. So, try to look at the database management system that is used for the database management for case-based surveillance, and then we'll look at the different tables we have and try to run examples of recreating those tables and understanding what the different constraints are that are enforced across the tables and why that decision was made. We have said previously that we have a file that uses the construct magic method to be able to run all of the queries to create tables within the database once a successful connection is established to the database that is specified. We define all of this within a function that uses this magic method. And what this does is that whenever anyone goes to the site and tries to log in, the first thing the system does is to check if there is a database that matches the name that is specified. Then it now checks again to see if the tables that are listed here exist in the database. And for the tables that have values to be inserted, if those values exist. If they do, it just skips creation and insertion, but if they don't, it's going to create a table and insert the records for tables that have default records. We said we have tables that we can call utility tables that hold information that just feeds the drop-down menu, and we store these things in tables so that the administrator can actually add and subtract without having to programmatically hard code these values as options on the forms. We insert into those tables by default some of the basic and first values that needs to be there, and then during configuration the administrator can add new values as it relates to the values that the country uses. I'll go back a little and redefine some terms just for those who are not fully IT or database administrators that are present here. When we talk about database, we have like something like an Excel spreadsheet that you can store values. When you write the headings for those values, those are the column. And when you now start putting data in those different rows, these are the rows of the information. Each data is a row of that information. That's exactly how a database is. It's just like an Excel spreadsheet. But when we now say we have a relational database, it now means that we are grouping related data together. Now, most of the time, when we have relational database, we need a relational database management system. And that's where MySQL came in. There are different types, there are different relational database management system. You choose what you want to use based on the functionalities, frequent reads, if you want to support more of transactions and all of those kind of stuff, and then see what system works for the kind of application. Now, while this was done in MySQL, countries are free to change, migrate, do whatever they need to do or want to do that fits whatever standards that is used within countries. So the classes file is that file where we have the definitions, and luckily all of structured query languages are just similar across the management system, and the changes that needs to be done to migrate from one to the other is just very minimal. We installed MariaDB, and from my understanding, MariaDB is just a lighter version of MySQL, or a free version of MySQL. And when you know MySQL, you already know MariaDB without some of those storage engines and all of those other things that slightly differs from one to the other. And so when I say MariaDB, it's basically MySQL we use, but we use MariaDB server and not MySQL server in the installation. So if you want to look at a database, you want to think about, or let's say a relational database, you want to think about, like, on your phones, you have a playlist, right, of all your favorite songs. And that playlist is a database because it holds data. The songs that you have will be related by different groups, whether they are blues or rocks or hip-hops and all of that. Now, in a database, information is structured. And because the data are related by nature, we call them relational database. So if you have all songs that are blues, are all categorized into blues, right? Because they're all related by nature. In the design of the case-based system, when the database was designed and we look at the forms or the data collection requirement, we had to make a decision on what group of data or what group of tables will be related that collects related information, and how do we keep the integrity between this table so it doesn't break. For instance, when we register a client, there are several tables that collect information from that registration. Let's look at the design of the client registration. I'm going to get the processing page for the personal information form, and we'll use that to illustrate. Okay, so this personal information form collects different information about the client, from the client's demographic information to information about the client's ID numbers, the country of birth and residence, and the health district, the parish, length of time in the country of screening, the marital status, highest level of education, and all of that kind of information. This processing page now looks at this data, and we have defined several tables to collect different information. We have a table that collects only information about the date of birth of the client. We have a table that collects information only about the gender of the client. Table that collects information only about the sexual orientation of the client. And then we have the table that collects only information about types of sexual activities, and then the table that collects information only about the risk behaviors of the client. Now, these tables are separated. Every table we have just holds certain information. For instance, the table that holds the residence of the client holds the country of residence, how long the person has resided there, if the person has moved out of the country or traveled out in recent time. Those information are all information around the client's residence and movement, and so it's stored in one table. Now, storing them in one table is like grouping data that are related in one table. But then this related data in one table is related to other data in other tables. And these are separated maybe for more easier maintenance and for the ease of locating things. But when it comes to filling a form that collects all of this information in one form, there has to be a way that we store this information or send them across the tables without breaking the integrity of the table. The index or the identity of each client on the system is the unique ID. Now, we have said previously that the unique ID can be any ID of the client. It depends on what the country wants to use. Some people use the hospital generated numbers, ID numbers of any government issued ID, whatever it is that countries use based on different regulations. But that ID uniquely identifies the client. And whenever you want to retrieve a client's record, you have to enter that ID. So it now tells us that the ID is the most important identity across tables. That ID is what will relate data from one table to the next. So out of the over 240 tables we have, we want to make sure that the data in table 1 knows that the data in table 200 belongs to the same person that is in line 1 of table 1 is the same person in line 5 of table 200. How do we know that? Then we begin to use the concept of foreign keys, where we have a primary table that is the parent, and then we have the child tables that are going to inherit from the parent. Now I'm trying to break down and describe the process for those that are not database administrator or in IT, just to grasp the concept before we look at the complexity of the design. The parent, when we say foreign keys, it sounds complex, but it is as easy as saying, okay, let's use a father for instance. A father is a parent. In some places, when a child is born, they use the father's last name, right? So in that family tree, we look at everybody who has that last name. Everybody with that last name are either children or descendants or siblings, but they have one parent and one source where that name started, and that is the parent. So the same thing in a database, the first table that has that definition is the parent table. Every other that use the same definition are children of that table. Once anything happens to that head, it tails down to the rest. The same thing in the database structure. Once anything happens to that parent table, it tails down to the rest depending on how you define it. If you say you want to cascade all delete, when the parent dies, the children dies. When the parent's name is changed, the children's name are changed. It is the same structure, exactly the same structure in database. So we have the concept of foreign key, where the parent table that holds the client registration information has the unique ID listed at the parent there. Every other table now lists the unique ID has a foreign key of that parent's table that holds the first registration. By design, you will now begin to see things like, once a client is registered, you want to now look at where the foreign key starts. We register the client here, and we have a first table that is the universal unique identifier table that we use. This matches a UUID to the unique ID. This becomes the parent of all the tables that exist in this database. If you want to wipe out all the records of a particular person, this is the table that you need to take that record out of, and it disappears everywhere. This unique ID is now listed in other tables. When the client is registered and some information are stored in this testing table, then we now have the unique ID listed as a foreign key, telling the system that you have to keep the integrity of this table by making sure that this unique ID here is related to the unique ID in the UUID table, and if you delete that, we want it to cascade. If you update that, you want it to cascade. Now, this is sample. Delete is going to be restricted in your live on your live servers, but on this we cascade the delete just for more testing. You can enter and remove, but on live, once it's entered, you can only update. You can't delete a record. All right. So everywhere we see this unique ID, we come to the address table. We have the address of the client, and then we have the unique ID as that ID that tells the data that this address on a particular row of the table in the address table is related, or is the address of the person in the other table that has that same unique ID. So when we want to get records across table, like we want to come to this testing table and get the gender, or let's say the type of test from the testing table, we come to the address and get the address and the health district and the parish. We come to the age table and get the date of birth. These are three tables that hold different information about the same client. And that unique ID now makes us know that when I go into the age table and I enter this unique ID, I'm going to be getting the date of birth of a particular client that I want. If I use that same ID on the education table, I'm going to be getting the highest level of education of the same client. So that is where the unique ID is important. And so for all clients, unique ID is the only way to retrieve their records, to do anything about the client's record. Again, this question has come up several times, and I'll answer it again before it is asked. The unique ID of a client is any ID the country chooses to use. There is no restriction. The system is going to accept whatever you use as a unique ID. It is not going to accept the same ID twice. So if one person has it, the next person that attempts to use the same ID will be rejected because that ID exists. It enforces uniqueness of each person on the system. So for countries that want to use the testing code that the lab generates, testing codes are not unique because in a country, you can find 100 people having exactly the same initials. And those initials are used in the same testing code algorithm, and it becomes exactly the same for several people. And so the first person with the testing code will have their account successfully created. The second person will have the creation failed because the system will say that this testing code already exists and you can't use it as a unique ID. You have to use a new ID. So there are no duplicate records on the system. The only duplicate you get is when you change the identity of a client completely. If you use a unique ID to register a client in one clinic and you use a different ID to register the client in another clinic, the system knows them as two different people. There is no magic that can happen for you to know that those two people are different because you decided to use different IDs for the same person. Does anybody have any question about that? All right, so we have those tables defined and separated. Now, for us to keep the integrity, there has to be a way where if a form is filled and that form has date of birth, it has gender, it has country of birth, country of residence, and this information is going to separate tables, different tables, and we want to make sure that we send them to all the different tables. We don't want to say we have fill the form and we send the information to, let's say for instance, 3 tables hold the same information. It is not the best type of design to hold the same information across several tables. You want information to exist once. But let's say this is an event where the system was already built before, new requirements came up, new tables are built. A particular column happened to exist in one table and the same information happened to exist in another table. And you want to enforce some integrity. Then at the point of data processing, where you collect the information entered into the field, you want to send this information in a transaction at the same time into all the tables. If you're updating, you want to do them at the same time. So here you see, we want to insert into a table called address change. At the same time, you want to update the address table. So when an address was specified for the client, and you fill in a form, and that form asks for the address of the client. And so you want to have a table that tracks all of the address change. At the same time, while you save that tracking, you also want to update the current address everywhere the addresses exist. And so you are going to be writing the queries so that it goes into all the table at the same time. And I am saying this for countries who will want to add new fields to their forms, and then you want to be sure to read the documentation to see if those fields need to go to other tables also, or if it breaks the surveillance report and it has to go into other certain tables to make sure that the report gets the information that they need. Or if you want it to be part of reporting, you have to make sure that all the tables that need that information is able to get the information, either by way of inserting new record or updating the existing one without overwriting the existing record. So we have this table that holds the current information and a table that holds the change logs of all of that information. So when I update an address of the client, it doesn't overwrite the address of the client. It just creates a new insert of a new address, and then when you come to the interface, you get the most recent address of that client displayed there. So whenever you want to track history of a client's address change, or you want to track history of a client screening, there is no overwriting of information. No information is lost. You can just always enter the unique ID and you get the whole history of all of the screenings and all of the addresses or anything you need to get the history for. Is it clear?
Yeah, it's clear.
Okay. Then we use something we call storage engine, and I will try to explain what that means. In MySQL, we have 2 types of storage engines. One is transactional and the other is non-transactional. All of the kind of operations that we do with the case-based surveillance system are transactional operations. And so we want to use a storage engine that supports transaction. And so we use InnoDB as the storage engine. If you look at the table definitions, you'll see that there's something called engine is equal to InnoDB. We also provide the character set and the collation that we want to use. During the database creation, you can also specify the character set and the collation. But I did that on all of the table definition, specifying the engine, the character set, and the collation that each of the table uses. InnoDB is the default storage engine. Even if you don't specify it for MySQL, you always have it there. And because it supports transaction and that integrity of data that we want to have, it makes it the best choice when developing this system. It supports foreign keys, which is what we want to use to make sure that data are related or tables are related. because many users are going to be inserting records at the same time. This same InnoDB supports what we call locking method. And it just means that only one user will alter a table at a time. So when two users click on submit at the same time, it will go one at a time. It's not going to, like, two of them are inserting exactly at the same time and cause any system conflict, even if it's a microsecond difference. So it offers that table locking method where only one will go, then the next will go through, and the next will go through. These things happen in microseconds that we don't even notice that it's that way. Now, you can choose to change your storage engine if you want to recreate your database and then change your engine. This will break the foreign key checks or the foreign key flow, and the integrity of the data at some point, if you're not careful, will now be violated. And that's the other type of storage engine, MyISAM, if you want to use that. Now we talk about character sets, and let me see, the best way to describe character set is like a set of symbols and encodings. And it's just, okay, let me explain both of them together so we can understand it. Like, a character set is a set of the symbols and encodings, and the collation is a set of rules for comparing the character in a character set. For instance, let's say we have two letters, X and Y. Let's say we say X is equal to 0 and Y is equal to 1. Now, because we say X is equal to 0, 0 is the encoding for X. And we say Y is equal to 1, 1 is the encoding for Y. Now, when we combine the two, we call it a character set. I don't know if this definition makes it easier. We have different languages. We have English, we have Spanish, we have several languages. There are different character sets based on the region that you're in. If I was reading this like strictly Spanish or Latin, I'll use a different character set. But UTF-8 is the best choice because it covers over 128 characters and symbols. So which means that when we have names that have diacritical marks and names that are tribal, it can accept and interpret correctly and accept those data because we are using a character set that can interpret and understand several languages and symbols. Is it understandable? So all of the different encodings is what we call the collation. And so there are a list of character sets that we have, and there's a list of the collation for those character sets that you can specify. For ECBS, the character set is UTF-8 and the collation is UTF-8 Unicode CI. You can change that based on, so if there is a Spanish-speaking country that is using the system, you can decide to say, while I'm installing, I'm going to change my character set and my collation for the table. And I don't want to use anything that general. I want to use the character set specific to the set of symbols and encodings that the language I'm going to be writing in supports. Does that make it clear? So in summary, UTF-8 has this multilingual support, and is just the best choice when we want to collect data of which we don't even know what all of the character set and collation will be. So this can be specified on the database creation, not just or not for the table creation, but we did them here just to make sure we have those things covered. Then we have different constraints that are enforced on the different tables. The most constraints you will find here are the unique constraint and the not null constraint. When a field is required on the form, you want to put those compliance checks and make sure that whoever is entering data into those form fields is going to keep to those rules that this data is required. And how do we define the required data? Data that are required for reporting, that are needed for the surveillance report. So we don't want to make the date of birth field optional. You can make the day and the month optional, but you want to be able to have a year of birth for analysis purpose. You don't want to make the biological sex or the sexual orientation or gender identity optional. You need these things for the risk behaviors. And so those are required fields. And because they are required on the interface, you want to make it required on the scripts that sends this to the database. And you want the database table column to enforce a not null constraint on the column that's going to receive that information. So that when you try to save and you don't fill in that field, it's going to throw everything out and tell you to fill in that field. So we have fields that must have data entered into it, and we enforce not null constraints on those fields. So when you add a new field on your forms and it is required that data is entered into that field, if the front end enables them to pass through, they enter it submit, and the back end, the scripting language, allows them to pass through, you want the database table to throw it out and not accept it because it doesn't want to accept null value in that field. And then they will immediately know that something has not been entered correctly. The error message will now define what it is that they're doing wrongly. And so they'll realize that they cannot move forward without filling in that required field. Then we have the unique constraint that we enforce on what has to be unique, and you don't want two of those values on the same table. So when you say the unique ID is unique, it means that you don't have the same person on the system twice. You can have the same person having different identities on the system. There is no way you can stop people from having different identities, but you can actually prevent the error of entering the same person twice, using the same ID 2 times. There is a request that people have asked that once you identify that 2 accounts are the same, can we merge them? The answer is yes, but the other answer is that the complexity is not worth it. And why I say so is people should just learn to do the right things from the beginning rather than work on errors, which will create more problems. If I see that these 2 people might be the same person, how do I merge the record of the 2 people? Now, these are very sensitive records and across several tables. If you are going to merge 2 information and those 2 information do not even have the same thing, the person's date of birth in information A is different from the date of birth in information B. The person's address in information A is different from B. One has to be supersede the other. One has to be the correct one, and one has to be the wrong one, or both of them are wrong. So there's no way to tell the system to do detective and say which of this is correct about the person, and when you merge, throw out the wrong one. So that makes it complexly impossible to want to merge 2 records correctly. What if we are merging 2 records that are actually not of the same person but are mistaken to be of the same person? How do the system warn you if we allow the merge? Which one supersedes the other? So at this point, while the merging is possible, does it keep the integrity of the information? No. And so there is no merging functionality. Once a particular particular patient exists more than once, and it is clear and identified it exists more than once, you delete the wrong one and leave the correct one. So we don't merge the two records. Okay? So for those that have asked the question, I'm just saying why that functionality was removed. There's no way to know which is correct and which is wrong. And there's no way to stop people from merging two people's records that are actually not the same, but because they see that the address is the same, the first letters of their credentials are the same, they happen to be screened around the same period, they happen to have the same height, it might just still be different people. All right. So we have these tables that are over 240, and some tables are tables that hold information for the patient management and reporting system, and some tables hold information for the virtual training workshop portal. The documentation will tell you what table belongs to what. When you see tables like the risk factor tables, the questions on the risk factor forms are too long and too wide that they cannot become column names. Like some tables, we can have them as column names and say, let's look at the residence table for instance. We can put column name, country of birth, column name, country of residence, and then column name, length of stay. This is easy to understand. If you go to that database table, you can easily know what column information hold. But you come to the risk factor table and you don't know what this is all about. So not all table column has their name according to the information that they hold. The documentation will hold documents about, or it will hold definitions about the different coding of this. When we say risk factor A, it means have the client had sex with males in the last 12 months. Risk factor B, has the client have sex with females in the last 12 months. Risk factor C, has the client had sex with persons of known HIV positive status. This coding will be put there because now it is so long you can't even write all of them as column names. And so when you want to export the risk factor table, for whatever reason, the reports are automatically generated already. But let's say there becomes a need to export that table. You begin to understand what each means. Maybe all you want to see is all of the people whose biological sex is male, whose gender identity is male, and who have had sex with male. Then you know that you are going to come to this table to get the risk factor A and column. You are going to go to the gender table to get the people whose sex is male. You are going to go to the gender identity table to see if the gender identity is still male. You want to go to the sexual orientation table to see if they are homosexual or heterosexual, and then you can use this across the tables to analyze. This analysis is done automatically again on the surveillance dashboard, but in the event that maybe for validation purpose, you want to export the records to be able to be double sure that the report that you get on the dashboard is exactly as accurate as you see it there. So you want to manually calculate. Or the only 2, 3, 4 sites in the country use the system, and you have records for more than 50 sites. And you know that doing it manually now supersedes. And all you want to do now is to export the raw record. So now add it to the calculation of the other ones you have gotten manually from the other site. That's where the use cases come in. So the documentation is thousands of pages. You will read them, you'll get tired of reading it, but you'll be able to find out from the index the information you need at the time you need them. You don't need to read the whole thing at once. You'll get them at the end of the training workshop. So we have a lot of tables like that where you don't understand what the column means. The definition of those columns will be stated clearly in the documentation. Okay? Before I continue, does everyone understand? Okay. So let's see an example of saying we want to create a new database. So let's say this system uses a database that the name is specified in the environment file. When you want to create a new database, and let's say we don't want to use a database that was created, we want to have, or we're trying to migrate our records to another database, but we don't want to delete the old database, and we want to create a new one and make sure that all these tables are created in the new database. Let's look at how to create the database, and then we'll read from it. We have a database called country, right? And this is the database that holds all of the tables for the case-based surveillance system. Now, we can see all the tables we have so far, and we can look at the different definitions of the table by coming to the structure. And we can see that what the collation is, we can see whether it accepts null or not, and we can look at the design. Let's go to this and get to the designer. This is going to be chaotic because it's a lot of tables, but when we have little tables or not so much tables, we'll be able to see how each table relates to the next by the lines that will be drawn for each table to show you where the table is connected to. So you see the table site name is connected to so many tables. We have so many lines going to the different tables, but not enough space on the screen for you to see all of it. Okay. Let's say we want to create a new database that will hold information, or we want to separate the whole case-based system into more than one database, and we don't want to delete the old one, but we want to have a new one, and then we'll start migrating records there. From what we have said, we write a simple query, right? The create database. So let's say we'll give this a new name because they can't have two the same name. We'll say create database. Now, because you don't want to have errors, you are doing this on your code, and you want to run it and not have to go to the log files to check why is this failing. You always want to check if that database name exists. If it already exists, you want to just go ahead and use it. If it does not exist, you want to create it. So we'll say create database if not exist, and let's say we want to create a database called, let's say, test country. So create database if not exist, test country, and then we want to say the character set. Let's say this time we want to change the character set. Let's say the character set will be UTF-8. You see UTF-8, let's just say MB4, and then we'll collate. Like this. So once I do this and I run, this will create my new database called test country. When I check here, I have test country here. So I have the database called test country created, but I have no tables in this database. But I want the case base to run on this, to create all the tables here automatically. I don't want to start creating the tables for the system. I will go to my environment file. Now, this is the directory structure. We say it is in the countries /country directory. And when we list here, we should see that we have .env file, which is the environment file. So now I want to open the environment file and tell them that my local environment where I am, I want to change the database name here to be the database name local to be test country, like this, and I'll save this. That's all you need to do. The environment file holds everything that you need. You change it. I come to the system now. And as soon as I try to log in, it will just go through creating all of the tables. And when I come back here, it has no tables, but when I click again, it has all the tables created automatically because I went to the home page of the Casebase system. So every time a user wants to use the system, they'll have to go to the home page. And then that check always happens. Does this have a database that is named? Does it have tables in it? Is it a first time use? I'll create it. If it has, then there's no problem. And then we'll have all the tables created here automatically. So now is it clear how the structure is automated? Is there anybody from IT here within the countries that have any question or query about the structure?
From St. Vincent. Hey, no, I don't have any questions at the moment.
Okay. All right, so when we come here, we'll now begin to see that there are tables and there are views. Now the definition of the views will also be stated. The views are just things we create to be able to put information in one place or aggregate information for us, so we can only run a select query against the views instead of having to have complex queries. So I know I want to get the age of a client at pregnancy, and we want when the antenatal system of that client, when the client's pregnancy ID is entered, you need the care card of the client or the antenatal card of that client to display the gestation age, the current age of the client. We need the system to be able to generate a flag for maternal risks, whether the age is under or above an age where the age becomes a risk factor. You need the system to be able to look at the age at pregnancy and be able to bring out other risk factors of maybe inadequate education, or if there are social factors included or to be checked for in the event of a minor. They want to look at age as screening again view. Is the one that will go across table and get the unique ID, get the age, and get the sex of the person, so that when we want to run analysis based on age group, we'll be able to see that, get all of the unique IDs from this age as screening view, where the age is a particular age, the sex is a particular sex, and that unique ID exists in the HIV records where all of the screenings are positive, things like that. So you begin to run those kind of queries. It makes it easier than trying to do them across 10 tables when you do them in the tables themselves. How do we define these views? In the same classes file where we have the database class and the table creation classes, we also have helper functions, and we have the definition of views that we have here. So at the end here, you will get the definition of views, and I think I'm going to change a lot of what you'll find in the documentation to make it even easier for someone who is not a database administrator but can navigate the computer to be able to work along with this. So we have the views created from tables. And so let's look at all the views we have, since they are not much. We have a view called, I'm not going to look at the views for the virtual training workshop platform because it will not make so much sense, but I'll look at the one for the patient management and reporting system. We want to get a view called age and screening, and we create or we replace view. Creation of views, you always want to create or replace, because the thing about views is when you change the database table definition, sometimes you need to change the view definition to be able to get that data, especially if you change the column names. I want to get age at screening, and I'm getting this from one table, but I need to perform an aggregate function on that table, and it's easier for me to do it and store it in a view than run that query all the time in a different file when I need that information across different files on the system. So I just do it in one place, collect it, and just run a select query against just that view. And so I have the age at screening, and when we define that, we just want to use an aggregate function sum to look at the date of the report and subtract the current year from it to be able to get the age of that report, the age of the person at the time of the report. If we want to get all the current age of the person, you want every year the age automatically updates. We have a view that calculates that current age to look at the current year we are in, and you subtract the year of birth of the person. So we begin to do all of these aggregate things outside of the code. We'll do them and store them as views. Views are like tables. They have the same namespace. They're exactly like tables, actually. Only that they get their data from whatever data is in the table. You can't do an insert or update operation to a view. You have to do it to the table itself. The view just pulls the records from the tables. Again, we want to have things like the sexuality of the clients. Now, because the clients have different mentality about their sexuality. Some people come and they tell you what they identify as. Some people come and they'll tell you that I'm a female, I identify as a female, right? What is your sexual orientation? I'm heterosexual. But then, have you had sex with males? No. Have you had sex with females? I only have sex with females. Then what they identify as and their risk behaviors are two different things. So we want a way for the system to be able to get the data that it needs without classifying people. And so we begin to create views like sexuality that will look at the person's biological sex, the person's gender identity, the person's sexual behaviors, and the person's gender identity, and the person's risk behaviors, and categorize this person as a male that has sex with males, female that have sex with females, and we begin to get our key population from those responses. I don't know if it is very clear for those that are the clinical management team. I don't know if that is the structure you use, or you just identify key population by what people say. If they say they are homosexual, you accept. If they say they are not homosexual, but they actually have sex with males. So what is actually the structure now? Is it any man that has sex with male is classified, or not classified, but the data is collected as MSM, or if he has sex with both males and female, he's not part of the MSM community? I don't know. I don't know if any of the doctors on the call can answer that, so that I'll be sure that that method is actually correct.
Yeah, for St. Kitts and Nevis, we based on the person's description. However, based on history taken, if the person have both sex with male and female, they are considered among the key population, and then we identify them as such.
Okay. All right. So that's what the system does now. It does not matter what the person responds. It looks at the person's biological sex, the gender identity, and the risk behaviors, and then collects the data as part of a group of the key populations. So the same thing that the views also look at the screened the risk behaviors of those that are screened and the risk behavior of those that are positive. So that's where you can get a visual of what risk behavior is most prevalent for people who tested positive. You see that everybody who has okay, so let's go to a surveillance dashboard and see how these views that are written here collect this multiple information and now displays it on the system. I don't know which countries are here with data in the system. We have Antigua. Karen, can I still use Antigua's surveillance dashboard?
Yes, you can, Mildred.
Okay, thanks.
You're welcome.
Okay, so we have things like we want to look at the risk behaviors of those that are positive, for instance. Let's look at year 2019. And I want to just show you how the views helps us to make this thing easier. Now we have, for instance, we have screenings by age group and sex. I want to look at where is the positivity by age group and sex. So you have those that are positive. That's for HIV. When we come to the views, we want to look at let's not look at positivity. We're looking for the risk behaviors. That will make us understand these views better. Let me see. Let's look at the behavioral report for 2019. Okay, so now we'll look at the risk behaviors of all those that are screened, right? And the most prevalent risk behavior we'll say is mostly illicit drug use. And then you now come to the risk behavior of those that are positive that was registered, and you see that the most prevalent risk is still illicit drug use, is still part of it. And then this begins to tell a story, right? And then the analysis is now easier by the visualization the system creates from the data that the system has. So at this point, you can choose to export this, or you can choose to come and identify the views that creates that report. So we have views that look at TB cases, for instance. It goes across the table to identify the person, goes to the care card to look at the diagnosis and the category, it goes to the screening to look at the type of test used and the results and the dates, and then puts them together and gives you a nice visualization to tell you about the cases. Maybe whether you want to disaggregate by different months of the year or by different time frames. So the same thing with the HIV cases. And then we look at where the risk behaviors, the view begins to collect this information, and then it begins to you see how long it is. You don't want to write this between your scripts. It becomes chaotic and it will lead to more errors. And so it's just easier to create a view in the database to already aggregate information, disaggregate information, or use aggregate function to perform extra things to give you extra columns that you need, that you can actually test for accuracy before you begin to use it in your code, right? So in the event you have new reporting indicators in the future, and you look at the documentation of which tables hold all of this information that you need if they're already being collected, the easiest bet is to just create a view as a new table that aggregates all of the information somewhere in the place. And if you can't build an interface for it, just export those information, because at this point you are not altering the design, the front end or the back end, or trying to do anything different. You are just trying to make the database create views that does this functionality automatically, and every time you come to export that view, you have all the information you need in one place. So is it now clear?
Yes, it's clear.
All right. So this is the whole summary of the database and the tables. We can't look at each of the table one after the other. If we want to know what this holds, we want to look at. So you just see the name can even give you exactly an idea of what it is. You know, it's about the syphilis for an infant. Is a perinatal syphilis clinical note. It holds all of the information of the clinical notes. For that, because of the name, you can easily infer what documentation will tell you what data each table holds. And then when you need to, and if the column definition is not clear, then there will be a definition for what that code is. These ones are clear. You see gestation age at birth, you know it's gestation age of that pregnancy before the child was born. If you see the reason for screening for the infant, you know the names like that. And for names that are not clear, there'll be an extra documentation for it. All right. Does anyone have questions before we end the session? All right. So in the absence of question, this is where this the agenda for the database ends. The video along with yesterday's video will also be made available as early as possible today, or maybe after the afternoon batch, and we'll meet tomorrow for the last one, which is the data and the encryption method used, so that we can have an understanding for the handover. So thank you everyone, and see you tomorrow.
Thank you, Mildred.
Yeah.
Thank you.